Hi and welcome to a lesson of multivariable calculus. Today's topic is constraint optimization problem using Lagrange multipliers. So where does the motivation for this problem comes from is that if you want to maximize or minimize some function of multivariable with some restriction, that is we have some constraint, then we can optimize by using the Lagrange multiplier method. So for instance, let's take an example that we are given a production function that is under some budget constraint, right? So we have a function that is a function of xy is given by x raised to the power 2 over 3 times y raised to the power 1 over 3, right? So where x and y are quantities of two raw materials, so therefore we are going to optimize this production function, right? So we have to maximize this function, maximize the product, but we have some constraint as well. That is, let's say, equals to x plus y is less than or equals to some constant, right? So the cost of these two raw materials should be restricted by this C, right? Now, when we are given a constraint, it means that these are two functions that can represent two surfaces geometrically, right? So we can see these functions. For instance, let's assume that if this function uh, is like this, for instance, this function, it's just for the sake of example, I'm drawing it like this. It's not necessarily the same as this function. And suppose if we have some other function which can be represented in this way, right? So there is something common in these two functions. Let me draw it again. Uh, let's draw it more clear. So the function somewhat look like this, right? So now in both of these functions, one represented by green and one represented by red, we have some common point that we called that we can call uh, a point where we can draw a tangent line, right? Now we can see that as this point is common between both of these curves. So if I want to find the gradient of both the functions at this point, so it is going to be parallel for both of the curves, right? So the gradients of both curves are going to be parallel to each other, and their magnitude can differ, but the function gradients will be parallel to each other, right? So let's say it's like this, or it may be in the downward direction as well, right? So the gradients of the functions are parallel. Therefore, if I represent the gradient of f by del f, then it's going to be some scalar multiple of the gradient of this function g, right? So this is the idea that Lagrange gave to solve the optimization problem restricted to constraints, right? Now, let us solve this problem, as we are already familiar with these terms. That what do we mean by gradient of a function? That is simply dou f over dou x. So it's a vector dou f over dou y plus dou f over dou z, right? So it's a vector function. Now let us start this solving this problem. So we are given with this constraint, that is this function that is represented by g. So we have two functions. F is equals x raised to the power 2 over 3, y raised to the power 1 over 3, and g represents x plus y is restricted by this c. And let's take this c as 3.78 as given in the problem. Now, first thing is that we need to find the gradients of these functions, right? So let us find the gradients. So you can see this graph as well here. It's drawn, the function is drawn. So this is the function that is x raised to the power 2 over 3, y raised to the power 1 over 3. So the level curves of the function are drawn, and then the budget constraint, that is the straight line, that is this line, and it cuts at single point. So the gradient at this point is going to be of both the functions is going to be parallel to each other, right? So now the gradient of f is going to be partial over partial x times the function, that is x raised to the power 2 over 3, y raised to the power 1 over 3, plus partial over partial y, x raised to the power 2 over 3, and x raised to the power, sorry, y raised to the power 1 over 3. Now if we find the partial derivatives of both these functions, we are just going to get 2 over 3 x raised to the power negative 1 over 3 y raised to the power 1 over 3 plus 1 over 3 x to the power 2 over 3 y to the power negative 2 over 3, and the gradient g is simply I plus j, since g is a linear function, right? Now, if we use the relation that del f equals lambda times del g, we are just going to get this thing is equals to lambda times this thing here, right? You can see here. So if these two vectors are equal, then their corresponding components are going to be equal. So we can write that 2 over 3 x raised to the power negative 1 over 3 y raised to the power 1 over 3 is going to be equals to lambda. Similarly, 1 over 3 x raised to the power 2 over 3 y raised to the power negative 2 over 3 is also going to be equal to lambda, because this thing here we can write it as lambda I plus lambda j, right? Now we can just simplify these two equations. So let's say this is equation 1, this is equation 2. We can solve these equations simultaneously. We can just divide these equations, so which leads to the function, uh, we will get the function uh, 2y equals to x by solving both these equations, that was equation 1 and equation 2. And then this equation is going to give the results for the variable x and y. So we have this equation to y equals x, which means y equals x over 2, right? Now we can use this constraint, that is x plus y equals 3.78, this equation with this equation to solve for x and y. If we plug in here y equals x over 2, so we get x plus x over 2 equals 3.78. So it gives 3x equals 2 times 3.78, and x equals 2 times 3.78 divided by 3. So from here we will get x equals 2.52, and then y equals 1.26. Now these are the two values of x and y which are going to maximize my budget function, my production function, that is given as x raised to the power 2 over 3 y raised to the power 1 over 3. So the maximum value of this function subjected to the constraint is going to be equals to, uh, let us write here, it is going to be 2.52 raised to the power 2 over 3, and y that is 1.26 raised to the power 1 over 3, and it's going to be 2. Right, so this is the way that we can optimize the functions of two variables. Now, let us move on to some interpretation of this lambda value, that what actually this lambda value defines. So, lambda is actually the Lagrange multiplier. So, what it says that is Now, if for instance, let us assume that if we are going to increase the budget, for instance, we have the budget as 3.78. Now, if we increase this budget by simple 1 unit, that is 4.78. Now, what happens here is that our previous lambda value subjected to this constraint was 0.53, for instance. Then if we increase the budget by 1 unit, then our uh, production is going to be increased by this much unit, right? So it means that if our production was f equals to 2, then we are going to get, say, f1 now subjected to this constant, it is going to be 2 plus 0.53. That is, it's going to be increased by the value of lambda. So it's going to be increased by lambda units, right? Since we increase the budget by 1 unit, so the production increased by the lambda unit, right? So this is the interpretation of this lambda value. Now, let us move to a problem where we have two constraints. For instance, let's take this one. Okay. Now we have this problem here, that is find the maximum value of this function, that is w equals x, y, z, and lying on the line of intersection of these two planes. So the constraints are now x plus y plus z equals 30 and x plus y minus z equals 0, right? Okay, let me clear one more thing, that in the previous example we have this inequality. So why we use this equality is because we want to use the maximum budget, right? So we can use the budget less than or equals to this one. So we need to maximize the production, we need to use the maximum budget. That's why we take this equality in the constraint, right? So here we are already given the equalities, right? So these equations, these are the constraints. Let's say this equation 1, this is 2, this is 3. Now we have three functions, right? Three functions. So again, the same concept, that the gradient of the function is going to be the scaled sum of these two uh, functions. Let's say this is g, this is h, and this is f, right? So plus mu times del g here, and mu times del f, del h, sorry. So now we are going to use this equation to optimize this problem, right? Because the gradients of all these three vectors are going to be parallel. Therefore, uh, by using simple linear algebra, we know that if three vectors v1, v2, v3 are parallel, then we can write these vectors as a linear combination of each other. Say v1 equals to alpha v2 plus beta v3, right? So we can do this thing here. Now here we need to find the gradients of these three functions. So first of all, we are going to find the gradient del w, then del g, and then del h, right? So this is actually w, so its function, we can set that a function of x, y, z, right? So now if we take the gradient of this function, that is del w, we are going to get y zi plus x zj plus xyk, and del g is going to be uh, I plus j plus k, and del h is going to be I plus j minus k. Now, taking these three equations into this simple equation and simplifying, we are going to just compare the coefficients. So we can say that y z equals lambda uh, plus mu, that is said call it equation 1. Then x z equals lambda plus mu. We call it equation 2. And then xy equals lambda minus mu, and call it equation 3. Now these are three equations we can solve simultaneously by just simply uh, subtracting 1 by 2. So we will get rid of this lambdas and mu. So if we subtract 2 from 1, we will get yz minus xz equals 0. So we will get x equals to y. Similarly, if we add 2 and 3, we will get xz plus xy equals to lambda. And again, if we subtract, add 1 and 3, we are going to get yz plus xy equals to lambda. Now we can use these equations to solve for x, y, and z. Therefore, let us just simplify these further. So x equals y, which means that if we use this x equals to y, let us clear this drawing first, and then so we have x equals to y, and then we can use two of the constants we already have, that is x plus y plus z equals 30, and the second constraint is x plus y minus z equals 0, right? Now we can use these two constants with this equation. So x equals y means from this equation we will get 2x plus z equals 30, and from this equation we are going to get 2x minus z equals 0. Now adding both the equations, we get 4x equals 30. That will give us x equals 15 over 2. Similarly, y is also going to be 15 over 2. And by using these two values in any one of these equations, we'll get the value of z. So let's do it here because this is simpler. So 15 over 2 plus 15 over 2 minus z equals 0, which gives z equals 30 over 2. So it's 15 over 2 plus 15 over 2 is equals to z. So we are going to get z equals to 15. So x equals 15 over 2, y equals 15 over 2, and z equals to 15. So these are the values that are going to optimize my function, that is w equals x, y, z, right? So the maximum value for w we are going to get is 15 over 2 times 15 over 2 times 15. So this will get 843 whole 3 over 4, right? Or just we can simply write in this form. So this is how we can solve these optimization problems by just simply using the concept provided by Lagrange, right? So we can solve these problems in n dimensions as well. If we have three constraints, then we can write it as lambda del g plus mu del h plus some other Lagrange multiplier times, say, del k. If we have one more constant, we call it k, right? So hope you guys understand this lesson. That's all for the time being. Thanks for watching the lesson.